What are your thoughts on Wireshark being a relevant tool for today? Do you think it's a skill set that someone in the networking or even cybersecurity space should focus on?
Well, you can't avoid it. I mean, if you're going to be serious about networking or cybersecurity or anything else, you have to know what's actually going on. And the only way you can do that is to see what the exchanges are, look at the attacks that somebody is making.
If you could send a space or a time machine back to the 70s, early 80s, when TCP/IP was first developed, what would you tell yourself to change? You are the original packet head. Packet people, thanks for coming back to the channel. I'm very excited to be here with Mr. Vint Cerf. He is here at the SharkFest Wireshark Developers and Users Conference here in Richmond, Virginia, 2025. Great to have you here, Vint. And I got the amazing privilege of sitting to do an interview with Mr. Cerf. So we're excited to have him tell us a bit about the internet, where it's been, where it is today, and where it's going for the future. So great to have you here, Vint.
Thanks so much. I enjoy these conversations.
So for those in the listening audience who might not be aware of the amazing work you've done, can you let us know your background?
Well, the simple thing is they can Google Vint Cerf. There's a Wikipedia article, but the short story is Bob Kahn and I started the design of the internet in 1973. It took us 10 years. We turned it on in 1983, and the rest is history. I've had something to do with the internet ever since then, so we're talking a 50-year career.
Yeah, so thanks for the humble answer. Honestly, you're one of the fathers of the internet, and it's such a privilege to have you here, like we mentioned. And so it's interesting thinking back at that time when you started that work. What was it that motivated the need? Like, what did you see as a need that the internet would address?
You know, I wish I could tell you that Bob and I woke up one morning and said, we're going to build the internet. In fact, it stemmed from an earlier project called the ARPANET, which stood for Advanced Research Projects Agency Network. ARPA was a part of the Defense Department. Their job was to avoid technological surprise because we had been surprised by the Russian Sputnik in October 1957. President Eisenhower was not happy about that, started this Advanced Research Projects Agency to avoid technological surprise. Somewhere along the line, ARPA started investing in artificial intelligence way back in the 60s. And they had a dozen universities that they were supporting to do research back then. But they all kept asking for the latest computing equipment. And of course, ARPA couldn't afford to buy 12 supercomputers every year. So they said, we're going to build a network and you have to share. And everybody hated that. They said, we're building it anyway. And they decided to use packet switching as the technology of the network. At the time, it was considered to be controversial, let's say, because everybody knew the way you build networks was circuit switching. That's how the telephone system worked. So we built this packet switch network called the ARPANET, and it really worked very well. Then Bob Kahn, who at the time had been at Volt, Beranek, and Newman, went to ARPA. Then the next thing that happens is that they start to think about using computers in command and control. But if you're going to do that, well, the computers are going to have to be in mobile vehicles, ships at sea, and airplanes, as well as fixed installations. And up till then, the ARPANET had been built out of dedicated telephone circuits connecting packet switches to each other. So Bob started working on a mobile packet radio network and a packet satellite network. By this time, I'm at Stanford University. And he comes out in the spring of 73 and he says, we have a problem. And my response was, what do you mean we? And he said, well, we worked on the ARPANET together. Now I've got this packet radio and packet satellite net, but they're all different. Delays are different. Data rates are different. Addressing structures are different. But we got to figure out how to hook them together and make it look all uniform. So for 6 months, we worked on that and came up with the notion of TCP, the Transmission Control Protocol. But then I moved to ARPA to run the program in 76. I promise I'm not going to go through 50 years of all this. And at that point, we realized that we needed to make some changes to the design. So we split the Internet protocol off from the end-to-end TCP protocol to create TCP/IP so we could do real-time speech and video and radar tracking and all these other things where you didn't have to get everything there. You just had to get it there quickly. You want to know where the missile is now, not where it was. So TCP/IP became the fundamental core of the internet. and we turned it on operationally in 1983. And ever since that time, I've had some relationship with the development of the program.
That is incredible. Wow, thank you for that background, that history. It's already filling in some questions that I already had. So we see where you started, and when these protocols were first envisioned, I would imagine you had no way of knowing where it would become today, or did you have a bit of an idea of what it would one day become?
Well, yeah, this is the question number 101. Did you have any idea that any of it be? An answer would be no, but it would be wrong. I think we had a sense that this was really powerful stuff. The experience with the ARPANET taught us a lot because we had maybe 50,000 people in the long run involved in research who had access to the network. Very shortly after we turned that on in 1969, the ARPANET, in 1971, electronic mail got invented by Ray Tomlinson at Bolt, Beranek, and Newman. This was networked electronic mail. And shortly after that, we had distribution lists. And the first two I joined were sci-fi lovers, where we could, argue over who were the best science fiction writers. And the second one was Yum Yum, which is a restaurant review thing that Stanford ran for the Palo Alto area. So you could see social networking in its very, very early stages out of email distribution lists. We also had remote access to time-sharing machines, and we had file transfers. So those were the primary applications up until around 1991, when Tim Berners-Lee announced the World Wide Web, which, of course, is another huge contribution to the world of networking. And, of course, it added another layer of protocol for Wireshark to go, decode. So by the time the World Wide Web shows up, and Mosaic, which was a graphical user interface version that came from the National Center for Supercomputer Applications around 1993, suddenly the world is ignited, as our networking world is ignited. Netscape Communications gets started in 1994, it goes public in 1995, and the stock goes through the roof and the dot boom is on. And so many of the people probably who are listening to this might have been around in the early 2000s as the dot boom becomes the dot bust. But there were companies that got started during that boom period that have survived and thrived. Examples, Amazon 1994 and Google 1998, just to name two. So in the intervening 25 years now, all kinds of things have evolved. And of course, today, if we weren't talking about artificial intelligence, we would have to, because it's come full cycle after several stages to the point where it's topic A these days.
Yeah, isn't it? I'm sure you're asked a lot about it. In fact, since we were on AI for the moment, you mentioned starting to work with AI back in the 60s. Did I hear that right?
That's right.
And how do you feel, since this has been decades of your life that you've seen it develop, what's different about now?
Oh, well, artificial intelligence went through 3 cycles, roughly speaking. The first version of it was called heuristic programming. What that means is that it didn't always work. If it worked all the time, it was engineering. If it doesn't work all the time, it's heuristic AI. But that didn't scale up very well. The next version was called expert systems. And this is a way of extracting detailed knowledge from someone in the form of if-then-else clauses. So, if this symptom shows up, then there's a probability of 30% that your patient has this disease, and then you should test. So you built up this huge array of if-then-else clauses, and after a while, they started contradicting each other, so it didn't scale very well. So, and there were periods of nuclear winter, so to speak, when some people didn't think AI was ever going to amount to anything. But there were a few people who hung on, especially the ones who were thinking about multi-layer neural networks. And so those had emerged as the fundamental mechanism for doing AI today. And now, of course, we're seeing some dramatic results with large language models. But even if we set those aside for just 1 second, their machine learning has also turned out to be a very powerful tool. It's not quite as elaborate as large language models. But what's interesting about it is that you can train a system to do things if the statistics of the thing you're training it to do have some stability. Example, we cool our data centers now with the help of AI. because we used to do it manually at figuring out how to change the valving and the pumping rates and so on to cool the data center to reduce the power requirements. Some poor engineer would try to do that once a week. We trained the system, a machine learning model, with a target of reducing the power required to cool the data center to save 40% of the power requirement as a result of using machine learning. And there are other examples of that, so like protein folding, a big example of that coming out of Google DeepMind. Then come these large language models. We've used those for language understanding, for speech understanding, speech generation, as well as language translation. Those are very powerful tools, and they're in regular use. And now, of course, we have generative AI, which is the latest instance of artificial intelligence. And that seems to be everywhere. And people speculate about what's going to happen as a result.
All right. So with Wireshark and on my channel, the viewers, they often stop by to look at TCP content, just because TCP is often something that they're troubleshooting.
Yeah.
Have you found that over your career and seeing it develop over time? What is it about TCP that's been difficult to troubleshoot as things have progressed?
Well, I think probably the hardest thing has always been flow control and buffer bloat. Those are the two performance issues that almost always arise. And it takes a lot of work to understand what's going on when throughput doesn't seem to be what it should be, or things get very congested. If you look at the history of TCP, you would note that at the beginning, it did not have a very sophisticated flow control mechanism at all. And over the years, people have developed more and more sophisticated mechanisms for doing flow control on an end-to-end basis. Van Jacobson, in particular, has contributed enormously to that. The buffer bloat stuff, David Tate was the one who really focused heavily on that. And sadly, he passed away recently. But lots of people remember him because of all of the hard work he put into figuring out how to eliminate the excessive delay caused by buffer bloat. So those are the two performance things that come up most.
Interesting. Did you ever expect TCP when it first started? I mean, here we're sitting 45 years later from when it was first in...
Really more like 50, because the first paper was published in May of 1974.
Wow.
In IEEE Transactions on Communications. And that was a description of TCP at the time. The implementations first started in 1975. So literally 50 years ago, we started implementing TCP.
So, I mean, what a testimony to its resiliency that it's still here after 50 years. Is that something that you envisioned?
Well, we hoped, of course, that it would serve its purpose. But you can see there have been new developments. QUIC is a very good example of that, running over UDP. And there are other parametric conditions where TCP or QUIC may not work adequately, and that's in high latency environments of deep space or highly disrupted environments. It's not clear. That's why we developed a new suite of protocols that we call the bundle protocol suite for delay and disruption tolerant networking, which we think will work better in these high latency and high disrupted environments.
Oh, because it's one thing... If I understand you correctly, it's one thing to go across an ocean; it's another to go to the moon.
That's or further. I mean, we have direct experience since the 1960s with deep space communications, and in particular with regard to Earth to Mars. Starting in 2004, our prototype software has been supporting the communications to the rovers since that time. And of course, the formal protocols, the bundle protocol suite has been evolving and is now at version 7, bundle protocol version 7, standardized by the IETF and also by the Consultative Committee on Space Data Systems. So this is serious stuff.
That is. All right, Vince, so let's come back down to earth. We are, if you want to.
Okay.
All right. I'm going to muscle it down. So we're at a Wireshark conference. I know you've seen Wireshark since its infancy and have known Gerald and the team. What were your thoughts when you first saw Wireshark as a visibility tool and troubleshooting tool, enabling people to visualize protocols in a new way? What were your thoughts back in the 90s when you first saw it?
Well, my first reaction was, what a fabulous tool, because things get really complicated, especially with multiple layers of protocol, large numbers of interactions taking place, and things happen. When you put things into the real world, you can never have tested for all possible conditions. I mean, when you click on a URL and you get a web page back, you just did an experiment that never happened in the history of the universe. And the reason I feel confident saying that is the state of the system is probably never repeatable. So no wonder when you're in the live internet, all kinds of weird things happen because you couldn't have tested for all cases. So Wireshark is this fabulous way of exposing what was actually going on. And so you could literally look at each of the exchanges and understand something about why one side didn't understand what the other side was doing. So it's super helpful for debugging. It's also helpful for improving performance, because you can see how systems can get all backed up because they were handshaking inappropriately or retransmitting too quickly or wasting resources. So the concept is fabulous, and it's applicable to an enormously broad range of exchanges that could take place. So I consider this to be an evolving and powerful tool. And you can tell from the number of people that come to the Wireshark conferences that they really care about this stuff.
That was my next question for you. We have a lot of new listeners from a new community of users. What are your thoughts on Wireshark being a relevant tool for today? Do you think it's a skill set that someone in the networking or even cybersecurity space should focus on?
Well, you can't avoid it. I mean, if you're going to be serious about networking or cybersecurity or anything else, you have to know what's actually going on. And the only way you can do that is to see what the exchanges are, look at the attacks that somebody is making, or try to figure out why a particular protocol, implementations of protocols don't work together. One of the big things about internet is that it's all protocol driven. Instead of one implementation everywhere, it's multiple implementations of the same protocols, but sometimes they don't get it right. And the only way to figure that out is to watch the interactions taking place. So Wireshark is, as a concept, is fundamental to the digital environment that we're in. We're not going away from that. Digital is here to stay.
So I have the rare opportunity to ask this question. It's one that I've had for you my whole career, but I'm just going to go ahead and ask it. If I
Go for it.
If you could send a space or a time machine back to the 70s, early 80s, when TCP/IP was first developed, what would you tell yourself to change?
Well, I'm sure that I would whisper into my 28-year-old's ear that you need 128 bits of address space for the internet. And I'm sure I would have laughed this old bugger out of the room. What do you mean 120? That's 2 to the 128 is 3.4 times 10 to the 38th addresses. I mean, that's a number only the Congress can appreciate. And besides, a 32-bit address space gives you 4.3 billion terminations if you allocate it densely enough. And that's more than there are people on the planet at the time. So I'm sure my 28-year-old self would have been very suspicious of that advice. The other thing that I might be tempted to whisper would be to say, you probably should pay a lot more attention to cryptography and security in the system. And my reaction at that point was twofold. First of all, the crypto of the day was not public key crypto. It was the conventional symmetric key. And key distribution is painful in that environment. That's what public key crypto did for us. It improved our ability to do key distribution. So at the time, I would have been resistant to putting in kind of crypto for safety and security. Also, the people who were doing this work were graduate students. That's the last group in the world that I would expect to do a good job of doing key management, because they're distracted by exams and final PhDs and all these other things. However, in 1976, two of my colleagues at Stanford with Diffie and Marty Hellman developed the concept of public key crypto. And of course, that took off within a few years, and that's what we use today. So I'm pretty sure I would have resisted that until this public key capability came along. And your listeners will know, that now we're threatened by quantum computing and the possibility of breaking the codes that are dependent on the difficulty of factorization of the products of large primes. But now we have a new set of protocols, thanks to the National Institutes for Standards and Technology, that will make use of something other than the difficulty of factorization. We're using lattice mathematics as the basis for these new algorithms, and those are not subject to attack by Shor's algorithm on the quantum machines. So crypto is here to stay, and we need it.
Okay, boy, that's an interesting message you would send back. So maybe even a 4-byte TCP window size, but yeah, that's another conversation. So it's been a great conversation with you. But, for our listening audience, we just want to let you know that Vint, he also suffers from real world problems, just like you and I do. In fact, you were telling me off camera that you had one just this morning. So what did you see, Vint?
I did indeed. I had just returned from San Francisco, flew on United Airlines, and I used my mobile to provide a hotspot for my laptop on the flight. And I got off the plane, went home, got up this morning, tried to print something, couldn't print it. And it said, printer not available, or printer is offline. I said, what the? So I checked with my other laptop, which I had left at home, and it was working fine, no problem. So I reboot my laptop, the one that can't find the printer. Then I reboot the printer, and I'm scratching my head, and then suddenly realized that the computer that couldn't find the printer was still using my laptop hotspot. And of course, it was on a network that wasn't the same as the network where the printers were. That took me half an hour to figure out, Phil. I'm embarrassed to tell you.
No, we appreciate you sharing the story, because I think all of us have those moments. So even a pioneer and father of the internet, everybody. Again, thank you, Vint. It's been nice to have some time to talk to you here at SharkBytes, and of course to have you here with the Packet people, because you are the original Packet head. Great to have you.
I've been called a lot of things before, but that's a new one.
Well, you're the first Packet person, so thank you. Thanks for the conversation.
Actually, I'm not the first Packet person. This is an important lesson.
He's not the first doing it.
Okay, yeah, I keep recording. First of all, Paul Barron, who was an engineer's engineer, was at Rand Corporation in the 1960s and was asked to look at how to create a network that would survive a nuclear attack. And he said, well, it's going to have to be a complex mesh with lots of connectivity and holes blown in it, and still allowing paths to be found from point A to point B. And so he developed what he called message blocks, which today we would call packets in packet switching. Then Len Kleinrock at MIT, a graduate student at the time, did his PhD on the statistics of message switching, which for all practical purposes are like the statistics for packet switching. And so he developed a queuing theoretic treatment of networks of queues that would help us anticipate and predict what the performance of these networks would be. And that got published as a book, and he went on to a tremendous career at UCLA as a professor. He's still there. He's still teaching. He's 90 years old and still going strong. So that's Len Kleinrock's part. And then Larry Roberts was the guy responsible for building the ARPANET, which used packet switching, which at the time was considered, controversial. And one other guy at the National Physical Laboratory, whose name I'm now blocking, which is embarrassing. I hate it when this happens. It'll come back. Well, in any case, let me give credit to the National Physical Lab in the UK for developing a packet switch network in the 1970s, early 1970s, to demonstrate that this was a good way for computers to communicate with each other. I hate this that I can't remember the name. This is awful.
You're doing great.
We have to go look it up.
It's going to come to you as soon as...
Donald W. Davies. There we go. Donald Davies is the guy at NPL. So those three people, Paul Barron, Len Kleinrock, and Don Davies, are the ones who are credited with developing the concept of packet switching.
Wow.
And we just jumped on that idea and used it.
So they're the original Packet people.
They're the original Packet people.
Wow, that's fantastic. So thanks for that history. So
you're welcome.
Again, then thank you very much for the interview.